Green buildings and architecture. Introduction: Building a greener tomorrow. We shape our buildings, thereafter they shape us. Winston Churchill. Sustainable designs. Our planet is at a tipping point. Climate change, resource depletion, urban sprawl and pollution are all symptoms of unsustainable development. Cities, while engines of human progress, are also major contributors to environmental degradation. The construction and operation of buildings alone account for nearly 40% of global energy-related carbon dioxide emissions. This reality has sparked a global movement toward green buildings, a shift from traditional construction to a new paradigm that values sustainability, efficiency, and human well-being. Green architecture is no longer a fringe idea. It's becoming the foundation for how we rethink our built environment, not just to reduce harm, but to actively restore ecosystems, promote health, and support resilient communities. This course is your guide to understanding how green architecture works, why it matters, and how it's transforming the way we live, work, and build. What is a green building? A green building is one that is designed, constructed, and operated to reduce or eliminate negative impacts on the environment and its occupants. It emphasizes efficient use of energy, water, and materials, healthy indoor air quality, and thoughtful site planning. But more than that, green buildings aim to enhance the quality of life, improve productivity, and promote well-being. Key aspects include energy efficiency, insulation, lighting, and systems that lower energy demand. Water conservation, low-flow fixtures, grey-water systems, and landscaping that minimizes water use. Sustainable materials, recycled, renewable, or low-impact materials used in construction. Indoor environmental quality, maximizing daylight, using non-toxic finishes, and ensuring proper ventilation. Site sustainability, minimizing disruption to ecosystems and integrating with the natural landscape. Green buildings are not one-size-fits-all. A rural eco-home, an urban high-rise, and a public library may all apply green principles differently, but the goal remains the same: to build with purpose and care. The evolution of green architecture. The roots of sustainable design run deeper than we might think. Ancient civilizations built homes using natural ventilation, passive solar heating, and locally sourced materials, not out of ecological concern but necessity and wisdom. Think of mud brick dwellings in Mesopotamia, thatched bamboo homes in Southeast Asia, thick adobe walls of Pueblo architecture. Fast forward to the 20th century. Industrialization and modernist design brought speed and innovation, but often at the cost of environmental health. It wasn't until the energy crises of the 1970s that architects began to seriously question the long-term consequences of wasteful, energy-intensive design. From those early days emerged pioneers like Frank Lloyd Wright, who embraced nature with organic architecture; Buckminster Fuller, who envisioned efficient, sustainable domes; Ken Yang, a Malaysian architect who introduced bioclimatic skyscrapers. Today, green building has gone mainstream. Innovations in technology, rising environmental awareness, and tightening regulations have helped create an architectural revolution, one that blends beauty, function, and responsibility. Why this course? This course isn't just about building codes or solar panels. It's about rethinking architecture as a tool for healing. Whether you're a student, an architect, a city planner, a builder, or simply a curious citizen, this course offers a solid understanding of green building principles, a look at the materials and technologies that make sustainable design possible, real-world case studies from around the globe, insight into emerging trends, such as regenerative design and smart cities. Most importantly, it aims to empower you. The buildings we design and inhabit reflect our values. If we want a sustainable future, we must start building it, literally from the ground up. What lies ahead? In the parts that follow, you'll explore everything from ancient passive design techniques to futuristic green skyscrapers. We'll dive into the technical aspects of energy and water management, examine landmark projects from every continent, and discuss the policies, challenges, and innovations shaping the future of sustainable architecture. Green buildings are more than structures. They are symbols of hope, creativity, and resilience. They remind us that design can be both beautiful and ethical, functional and inspiring. Let's begin the journey toward a greener world. Part 1: Core Principles of Green Architecture. Sustainability is not a feature, it's a responsibility. Green architecture isn't just about adding solar panels to a roof or planting a few trees around a building. It's about a deep, integrated approach to design that respects the planet, the people who use the building, and the materials used to construct it. At its heart are a few core principles, essential elements that form the DNA of any truly sustainable building. In this part, we'll explore the 5 major pillars of green design: energy efficiency, water conservation, material efficiency, indoor environmental quality, sustainable site development. 1. Energy efficiency, doing more with less. Energy is one of the biggest drivers of environmental impact in buildings. Heating, cooling, lighting, and powering our built environment uses massive amounts of energy, often from fossil fuels. Green architecture tackles this head-on through energy-efficient design, which includes high-performance insulation and windows to prevent heat loss gain, passive solar design, using building orientation and materials to naturally regulate temperature, energy-efficient HVAC systems, lighting, and appliances, renewable energy integration, such as solar panels, wind turbines, or geothermal systems. Energy efficiency isn't just about reducing carbon emissions, it's also about long-term cost savings and resilience. A well-designed green building stays comfortable with less reliance on the grid, especially important in the face of energy shortages or climate-related disruptions. 2. Water conservation, every drop counts. Water is becoming one of the most precious resources of the 21st century. Droughts, pollution, and overuse threaten freshwater supplies worldwide. Green buildings aim to use water wisely and recycle it wherever possible. Key strategies include low-flow faucets, showerheads, and toilets that reduce water use without compromising performance. Rainwater harvesting systems to collect and reuse water for landscaping or non-potable uses. Greywater recycling, which reuses wastewater from sinks or showers for irrigation. Drought-resistant landscaping, also known as xeriscaping. Some cutting-edge green buildings go even further with net zero water goals, producing or recycling as much water as they consume. 3. Material efficiency, building smart, building less. The choice of materials is a major component of green design, not only for their environmental footprint, but for their health impacts and durability. Green architecture promotes recycled and reclaimed materials, like steel, glass, and wood. Rapidly renewable resources, such as bamboo or cork. Local materials to reduce transportation emissions. Non-toxic finishes that don't off-gas harmful chemicals. Modular and prefabricated construction to minimize waste. The goal is to use fewer resources, generate less waste, and support responsible supply chains. Every material used in a building tells a story. Green buildings ensure it's one worth telling. 4. Indoor environmental quality, IEQ, health from the inside out. While much of green architecture focuses on environmental impact, it also prioritizes the health and comfort of the people who use the space. Key aspects of good IEQ include clean air, free from pollutants, mold, and volatile organic compounds (VOCs). Natural lighting, which supports circadian rhythms and reduces energy use. Thermal comfort, achieved through thoughtful design and system control. Acoustic comfort, minimizing noise pollution from both inside and outside. Studies have shown that buildings with high IEQ improve productivity, reduce absenteeism, and even enhance mood. In short, a green building doesn't just protect the planet, it nurtures the people inside. 5. Sustainable site development, building in harmony with nature. Where and how a building is placed can have massive environmental consequences. Sustainable site development is about choosing locations and design strategies that preserve ecosystems and reduce environmental strain. This includes minimizing land disturbance and protecting local habitats, reducing heat island effects with green roofs or reflective surfaces, encouraging public transit access, biking, and walkability, managing stormwater runoff to prevent erosion and water pollution. Sustainable site planning also considers the community impact of a project. Does it promote equity, accessibility, and connection to nature? A truly green building supports not just the environment, but the urban or rural fabric around it. The whole systems approach. Each of these 5 principles is powerful on its own, but the magic happens when they work together. This is called the whole systems approach, where energy, water, materials, and health are all interdependent and designed in concert. A green building isn't a checklist. It's a mindset. It's about seeing the built environment not as an isolated object, but as part of a living, breathing ecosystem. Part 2: Green Building Certifications. You can't manage what you don't measure. Peter Drucker. Sustainability isn't just a feel-good concept, it needs to be measurable, verifiable, and accountable. That's where green building certifications come in. These systems provide standards and benchmarks for evaluating the environmental performance of buildings across categories like energy, water, materials, health, and innovation. Think of certifications as a report card for green buildings. They offer designers, builders, and owners a framework to follow, while helping occupants and investors understand a building's environmental value. Why certifications matter. Certifications do more than just offer bragging rights. They encourage best practices in sustainable design and construction, increase market value, and attract eco-conscious tenants or buyers, often qualify buildings for tax incentives, grants, or fast-track permitting, provide a recognized standard across regions or industries, promote transparency and accountability in sustainability claims. Let's explore 5 of the most widely recognized green building certification systems in the world. 1. LEED, Leadership in Energy and Environmental Design. Origin, USA, developed by U.S. Green Building Council, USGBC. Overview. LEED is perhaps the most globally recognized green building rating system. It uses a point-based system, awarding certifications at certified silver, gold, or platinum levels. Categories evaluated: sustainable sites, water efficiency, energy and atmosphere, materials and resources, indoor environmental quality, innovation in design, regional priority. Why it's popular? LEED is flexible, applicable to many building types, offices, schools, homes, neighborhoods, and widely used in over 160 countries. It also emphasizes continuous improvement. Buildings must be maintained to keep their status. 2. BREEAM, Building Research Establishment Environmental Assessment Method. Origin, United Kingdom, developed by Bray Group. Overview. Introduced in 1990, BREEAM is one of the earliest green building rating systems. It's known for its rigorous scientific approach and adaptability to local conditions. Assessment areas: energy, health and well-being, innovation, land use, materials, management, pollution, transport, waste, water. Rating levels: pass, good, very good, excellent, outstanding. Key strength: BREEAM places a strong focus on the management of environmental performance, making it especially valuable for long-term operational sustainability. 3. Well Building Standard. Origin, USA, developed by International Well Building Institute, IWBI. Overview. While most green certifications focus on environmental impact, WELL is centered on human health and wellness. It complements other certifications like LEED. Key areas: A. Water, nourishment, light, fitness, comfort, mind, community, innovation. Notable feature: WELL certification requires performance testing, such as indoor air quality and lighting levels, verified by third-party professionals. Why it matters: in a world where people spend 90% of their time indoors, WELL's people-first approach is becoming increasingly relevant, especially post-COVID. 4. Living Building Challenge, LBC. Origin, USA, developed by International Living Future Institute, ILFI. Overview. The Living Building Challenge is the most ambitious and holistic green building certification out there. It challenges designers to go beyond less harm to creating buildings that are regenerative. 7 Performance Petals. Place, water, energy, health and happiness, materials, equity, beauty. Unique feature: certification is only awarded after 1 year of occupancy and performance tracking. It's not just about theory, it's about results. Goal: net zero or net positive energy, water and waste. It's a certification for those aiming to build the greenest buildings on Earth. 5. GRIHA, Green Rating for Integrated Habitat Assessment. Origin, India, developed by the Energy and Resources Institute, TERI, with the Indian government. Overview. Tailored to India's climate and developmental needs, GRIHA evaluates how efficiently buildings use resources across their life cycle. Evaluation criteria: site planning, energy optimization, waste management, renewable energy, water efficiency, occupant comfort and well-being. Importance: GRIHA bridges modern green building practices with regional realities, making sustainability more accessible in developing economies. Choosing the right certification. There's no one-size-fits-all certification. The best choice depends on location and climate, type of building, residential, commercial, institutional, etc., budget and resources, focus, environmental impact versus human wellness versus net zero goals. Some projects even pursue dual certification. For instance, a building may be both LEED Gold and WELL certified to showcase environmental and wellness achievements. Certifications as catalysts. Beyond the rating plaques and point systems, these certifications have catalyzed a global transformation in how we think about buildings. They've pushed the industry to innovate, compete, and raise standards across the board. Even projects that don't seek certification often adopt these guidelines as best practices. Ultimately, certifications are tools, not trophies. They help measure progress, set targets, and hold the industry accountable for its environmental footprint. Part 3: Eco-friendly building materials. The materials we choose today shape the future we live in tomorrow. A building is only as sustainable as the materials it's made from. Every wall, floor, beam, and finish leaves a mark on the planet, from the resources it consumes to the waste it generates. In green architecture, materials aren't just functional, they're strategic. They reflect a conscious choice to reduce environmental impact, enhance performance, and even promote occupant health. In this part, we'll explore the characteristics of eco-friendly materials, a breakdown of popular sustainable materials, considerations for sourcing and life cycle impact, how material choices affect green building certifications. 1. What makes a building material green? Not all sustainable materials look the part. Some are natural and earthy, others are high-tech and engineered. What defines a material as eco-friendly isn't how it looks, it's how it behaves across its entire life cycle. Key characteristics of green materials: renewable or abundant, can be quickly replenished, e.g. bamboo, or easily reused, e.g. steel. Low embodied energy, requires minimal energy to extract, produce and transport. Non-toxic, free from harmful chemicals and VOCs that can affect indoor air quality. Durable and low maintenance, reduces the need for replacement or repair. Recyclable or biodegradable, doesn't end up in a landfill after use. It's not just about the product, it's also about the process, how it's harvested, who's producing it, and what happens at the end of its life. 2. Popular eco-friendly building materials. Let's explore some of the most widely used, and some emerging green materials in architecture today. Bamboo. Why it's green: grows rapidly, up to 3 feet a day, requires no fertilizer and regenerates after harvesting. Uses: flooring, cabinetry, paneling, structural components. Bonus: stronger than steel by weight and naturally antibacterial. Rammed earth. Why it's green: made from compacted soil and stabilizers like lime or cement. Uses: walls with high thermal mass, excellent for hot climates. Look and feel: natural textural finish that's both ancient and modern. Hempcrete. Why it's green: made from hemp fibers and lime, carbon negative and breathable. Uses: wall insulation, thermal and acoustic buffering. Fun fact: hemp grows fast and cleans soil as it grows, a win for agriculture and architecture. Recycled steel and aluminum. Why it's green: highly durable and infinitely recyclable with minimal quality loss. Uses: framing, roofing, facades. Energy savings. Recycled steel uses 75% less energy than new steel production. Reclaimed wood. Why it's green: keeps wood out of landfills, reduces demand for new lumber. Uses: flooring, beams, furniture, paneling. Aesthetic bonus: weathered, textured and full of character. Fly ash and slag concrete. Why it's green: industrial waste byproducts that can replace cement, which is highly carbon intensive. Uses: foundations, structural elements, pavers. Impact: reduces CO emissions from concrete production. Low VOC paints and finishes. Why it's green: reduces indoor air pollution and off-gassing. Uses: walls, cabinetry, trim. Health factor: VOCs are linked to headaches, respiratory issues and worse. These options eliminate that risk. Cork and linoleum flooring. Why they're green: cork is harvested without cutting down the tree. Linoleum is made from linseed oil, wood flour and jute. Uses: flooring in schools, hospitals, offices. Durability: naturally antimicrobial, resilient and soft underfoot. 3. Local sourcing and life cycle thinking. Green building materials aren't always about what's in trend, they're often about what's local. Materials sourced nearby. Reduce transportation emissions. Support the local economy. Are often better suited to the climate. This is called regional appropriateness, a key principle in sustainable design. Another big concept is life cycle assessment, LCA, looking at the total environmental cost of a material from cradle to grave, or better yet, cradle to cradle. The greenest material isn't always the one that seems eco-friendly, it's the one that performs best over time with the least impact. 4. How materials influence certifications. The choice of building materials significantly impacts green building certifications like LEED, awards points for recycled content, local sourcing, rapidly renewable materials and low VOC products. BREEAM emphasizes responsible sourcing and life cycle analysis. Living Building Challenge has a red list of prohibited toxic materials and promotes only safe, ethical and regenerative materials. WELL focuses on the health implications of materials, particularly indoor air quality and toxin exposure. In other words, choosing eco-friendly materials isn't just about being sustainable, it's also essential for achieving high performance ratings. The future: bio-based and smart materials. Material science is evolving fast. The next wave of sustainable materials includes mycelium, fungus-based insulation and packaging. Transparent wood, a possible alternative to glass. Self-healing concrete. Phase change materials for passive temperature regulation. These innovations push us closer to buildings that don't just reduce harm, they regenerate ecosystems and respond to environmental conditions. Part 4: Passive Design Strategies. A truly sustainable building uses the forces of nature to its advantage. You can load a building with energy-saving tech, but one of the most powerful tools in green architecture is also one of the oldest: passive design. Passive strategies don't rely on mechanical systems or gadgets. Instead, they use natural energy flows for sunlight, wind, and thermal mass to heat, cool, and light buildings efficiently. Before air conditioners and LEDs, civilizations used passive design principles out of necessity. Now we're returning to them with better data, tools, and purpose. This part covers what passive design is and why it matters. Key passive strategies for energy savings. Regional variations in passive design. Passive house standard. Integrating passive and active systems. 1. What is passive design? Passive design is about designing buildings that work with the climate, not against it. Instead of adding systems to fix temperature or lighting problems, passive buildings are shaped to avoid those problems in the first place. Core goals: maximize natural daylight, maintain comfortable indoor temperatures year-round, minimize energy use for heating, cooling, and lighting. When done right, passive design can cut a building's energy consumption by up to 70%, all while improving comfort and reducing mechanical dependence. 2. Key passive design strategies. Building orientation. North-south orientation in the northern hemisphere optimizes exposure to sunlight. South-facing windows get consistent daylight in winter and can be shaded in summer. Minimizing east and west glazing helps control heat gain from the low-angle morning and afternoon sun. Passive solar heating. Letting sunlight in during winter through south-facing glass. Thermal mass, like concrete or stone floors, absorbs heat during the day and releases it at night. Natural ventilation and cross-ventilation. Strategically placed windows and vents pull fresh air in and push hot air out. Stack ventilation uses vertical spaces, like stairwells, to create a chimney effect. Thermal mass. Dense materials, stone, concrete, brick, stabilize indoor temperatures by absorbing and releasing heat slowly. Used with passive solar heating to reduce reliance on HVAC systems. Shading and overhangs. Roof overhangs, louvers, awnings, and vegetation block summer sun but allow winter sun to enter. Trees can act as natural climate controls. Deciduous trees shade in summer, go bare in winter. Window placement and glazing. Well-placed windows bring in daylight and enable airflow without overheating the space. Double or triple glazing improves insulation and reduces unwanted heat gain loss. Daylighting design. Light shelves, clerestory windows, and reflective surfaces spread daylight deeper into interiors. Reduces the need for artificial lighting, improving mood and energy efficiency. 3. Climate-specific design. Passive design is not one-size-fits-all. It must respond to local climate conditions. A building in New Mexico will look and function very differently than one in coastal Norway. The most sustainable building is the one most adapted to its place. 4. The passive house standard. Passive house. Developed in Germany in the early 1990s, the passive house standard is one of the most rigorous energy efficiency standards in the world. Key features: super insulated walls and roofs, High-performance windows and airtight construction. Heat recovery ventilation (HRV) for clean indoor air. Ultra-low energy usage for heating, cooling, often as little as 15 kWh per square meter per year. Though it requires precision design and construction, the results are impressive. Passive houses consume up to 90% less heating energy than conventional buildings. Bonus: the concept is now being adapted to warm climates too, not just cold European winters. 5. Blending passive and active systems. While passive strategies do a lot, most modern buildings use a hybrid approach. Passive first, optimize shape, orientation, insulation and airflow. Active second, add solar panels, heat pumps or smart systems to fine-tune performance. This balance creates buildings that are low energy by design and zero energy by technology. Passive strategies reduce the load, and active systems meet the load efficiently. Real-world example: the Bullitt Center, Seattle, Washington. Often called the greenest commercial building in the world, the Bullitt Center uses south-facing solar panels, deep overhangs for shading, operable windows for natural ventilation, geothermal heating and high thermal mass. It combines passive and active design to achieve net positive energy and water use. Why passive design matters. Low tech, low cost. Many passive strategies are cheap or free with thoughtful planning. Durability. Passive systems don't wear out the way machines do. Resilience. When the power goes out, passive buildings stay more comfortable. Comfort. Fewer drafts, more daylight, and better indoor air equals happier occupants. Passive design connects us to time-tested wisdom and modern performance goals, showing that the smartest solutions are often the simplest. Part 5. Energy systems and smart technology. A sustainable building doesn't just use less energy, it knows how to use it better. Passive design strategies create a strong foundation for energy efficiency. But to go from low energy to zero energy or even energy positive, buildings need smart, active systems that generate renewable energy, monitor consumption and adjust performance in real time. In this part, we explore renewable energy systems for buildings, smart building technologies, net zero and net positive buildings, energy storage and grid interaction, the role of data and automation. 1. Renewable energy systems. To be truly sustainable, a building must minimize its carbon footprint by drawing energy from clean, renewable sources. Let's break down the most common systems. Solar photovoltaic (PV) systems. What it is: panels convert sunlight directly into electricity. Why it matters: widely available and scalable. Lower costs and improved efficiency in recent years. Roof and facade installations reduce need for external land. Battery storage, e.g. Tesla Powerwall, lets buildings use solar power at night or during outages. Solar thermal systems. What it is: uses solar collectors to heat water for domestic use or space heating. Great for residential and small commercial buildings, especially in sunny climates. Geothermal heating and cooling. What it is: ground source heat pumps draw heat from the earth in winter and transfer heat back in summer. Benefits: stable temperatures underground, offer high efficiency year-round. Minimal surface footprint. Long system lifespan, 20 to 50 plus years. Wind turbines. What it is: turbines convert wind into electricity. Note: most suitable for rural or coastal locations with consistent wind speeds. Emerging tech: small-scale vertical axis wind turbines (VAWTs) for urban use. Combined heat and power (CHP). What it is: simultaneously generates electricity and useful heat from a single energy source. Best for industrial or campus-scale developments. 2. Smart building technologies. Energy systems are only as efficient as the technology that manages them. Smart buildings use digital tools to optimize performance in real time. Sensors and IoT, Internet of Things. Occupancy sensors, turn off lights HVAC in unoccupied areas. Daylight sensors, adjust lighting levels automatically. Air quality sensors, trigger ventilation or alerts. Energy meters, track real-time usage by zone or system. Building management systems (BMS). Centralized platforms that monitor and control HVAC, lighting, water use and security systems. Advanced BMS features. Predictive maintenance alerts. Energy performance benchmarking. Integration with weather data for dynamic adjustments. Smart thermostats. Devices like Nest or Ecobee learn usage patterns and respond to occupancy and outdoor conditions. Energy savings, up to 20% reduction in HVAC energy use. AI and machine learning. Future-forward systems use AI to forecast energy demand, optimize energy distribution, identify inefficiencies, automatically adjust settings for occupant comfort and efficiency. 3. Net zero and net positive energy buildings. A truly green building doesn't just use less energy, it produces as much or more than it consumes. Net zero energy building (NZEB) produces as much renewable energy as it uses annually. Typically combines passive design plus high-efficiency systems plus on-site renewables. Examples: offices, schools, homes, even entire net zero neighborhoods. Net positive energy building goes beyond net zero by generating more energy than it uses. Excess can be sold back to the grid or stored for future use. Incentives, utility credits, government subsidies, and energy independence. 4. Energy storage and grid interaction. Renewable energy is great but intermittent. That's where storage and smart grid interaction come in. Battery storage stores excess solar wind energy for use at night or during peak demand. Improves energy resilience, important in areas prone to outages. Key technologies: lithium-ion flow batteries, saltwater batteries. Demand response and smart grids. Buildings communicate with the electrical grid to reduce consumption during peak hours. Some systems even shift usage to times when clean energy is more available. Benefits: saves money, reduces strain on the grid, supports renewable integration at scale. 5. The role of data. In the smart building of the future, data is gold. Performance dashboards. Real-time feedback on energy, water, temperature, air quality and occupancy helps. Facility managers make informed decisions. Occupants change their habits. Owners verify that systems are working as designed. Post-occupancy evaluation (PO). POEs compare design expectations with real-world performance. They're essential for identifying performance gaps, fine-tuning building systems, informing future projects. Certifications like LEED and WELL increasingly require or encourage PO. Case Spotlight: The Edge, Amsterdam, Netherlands. Dubbed the smartest building in the world. Solar-powered, net zero energy. 30,000 sensors track lighting, temperature, humidity, occupancy. Smartphone app assigns hot desks and adjusts personal lighting preferences. BMS fine-tunes building conditions based on real-time data. The Edge proves that technology and sustainability can create buildings that are adaptive, efficient, and even fun to occupy. Part 6: Health and Well-being in Green Buildings. The greenest building is not just energy efficient, it's human-friendly. Sustainability isn't only about saving the planet, it's also about supporting the people who inhabit buildings every day. A truly green building considers air quality, natural light, acoustics, comfort, and psychological wellness as essential components of good design. In this part, we explore the connection between sustainability and human health. Key design elements that influence well-being. Indoor air quality and ventilation. Lighting, circadian rhythms, and access to nature. Health-focused building certifications. 1. Sustainability and human health, a natural partnership. Green buildings often benefit people in ways that go far beyond utility bills. According to studies from the World Green Building Council, green-certified buildings have been shown to improve productivity by up to 11%, reduce employee sick days, increase cognitive function scores, enhance occupant satisfaction. These outcomes are especially important in homes, offices, schools, and hospitals, where indoor environments shape long-term well-being. 2. Design elements that support wellness. Let's break down the key design features that promote a healthier indoor environment. Air quality. Eliminate indoor pollutants like VOCs, volatile organic compounds, mold and off-gassing materials. Provide effective filtration systems, e.g., MERV-13 filters or HEPA filters. Ensure fresh air through natural or mechanical ventilation. Daylight and views. Natural daylight enhances mood, focus, and circadian rhythm. Windows with outdoor views reduce stress and boost satisfaction. Daylight design should avoid glare and overheating. Biophilic design. Connect people to nature, using natural materials, textures, and colors. Include green walls, indoor plants, or access to outdoor spaces. Mimic nature through lighting, sound, and form. Thermal and acoustic comfort. Maintain consistent indoor temperatures without drafts or cold spots. Use materials and design strategies to reduce unwanted noise. Empower occupants to adjust their own comfort settings, thermostats, windows, fans. Personal control and adaptability. Spaces that allow for user input, e.g., adjustable blinds, operable windows, personalized lighting, create a sense of comfort and autonomy. Flexibility in furniture, layout and lighting supports different working styles and physical needs. 3. Indoor air quality IAQ, breathing easier. Most people spend 90% of their time indoors, making indoor air quality crucial to health. Sources of indoor air pollutants include building materials, paints, adhesives, carpet glue. Furnishings, foam, laminates, finishes. Office equipment, printers, copiers. Poor ventilation and moisture problems. Green solutions. Choose low VOC or zero VOC materials. Install demand-controlled ventilation that adjusts based on CO levels. Incorporate air-purifying plants and UV air sterilizers. Maintain optimal humidity levels, 30 to 50%, to prevent mold and bacterial growth. 4. Lighting and the human body. Light impacts our sleep, mood, and hormonal balance. Poor lighting can disrupt circadian rhythms, cause eye strain, and contribute to fatigue. Key lighting strategies. Use full-spectrum LED lighting that mimics natural sunlight. Design for daylight autonomy, reducing need for artificial light during the day. Align workspaces and bedrooms with the body's natural sleep-wake cycle. Include task lighting and allow for user adjustments. Circadian lighting systems, now available in smart buildings, adjust light temperature and brightness throughout the day to support healthy rhythms. 5. Access to nature and biophilia. Nature heals. That's not just a nice idea, it's backed by science. Benefits of biophilic design. Reduce stress levels. Enhanced creativity and cognitive function. Lower blood pressure and heart rate. Faster healing times in hospitals. Strategies include incorporating natural materials, wood, stone, clay. Using natural patterns and forms in finishes and furnishings. Creating visual and physical access to outdoor environments. Installing green roofs, courtyards, or garden walls. 6. Health-focused building certifications. Just like energy and sustainability have LEED and BREEAM, human-centered design has its own certification systems. WELL Building Standard focuses on health and wellness of occupants. Covers air, water, nourishment, light, fitness, comfort, and mind. Requires post-occupancy testing and monitoring. Often paired with LEED for holistic green certification. Fitwell. Simple, scalable certification. Backed by the CDC. Emphasizes workplace health, access to fitness and social equity. Designed for both new and existing buildings. Reset Air. Performance-based indoor air quality certification. Continuous monitoring of CO, VOCs, PM2.5, humidity and temperature. Especially valuable for dense urban areas and health-sensitive buildings. Case study: Phipps Center for Sustainable Landscapes, Pittsburgh, Pennsylvania. Designed to meet LEED Platinum, WELL Platinum, and Living Building Challenge standards. Features natural ventilation, indoor green walls, and a restorative garden. Uses biophilic design principles throughout. Staff report lower stress, better focus, and higher job satisfaction. Final thoughts: a building that loves you back. Sustainable design isn't just good for the earth, it's good for the mind, body, and soul. By designing spaces that support health and happiness, we unlock the true potential of architecture to create places that make life better. Whether it's a child in a classroom with daylight and fresh air, a patient healing faster in a biophilic hospital, or a worker thriving in a clean, quiet, flexible office, green buildings are human-centered buildings. Part 7. Sustainable Urban Design and Planning. A building doesn't exist in isolation, it's part of a neighborhood, a city, a world. Sustainable architecture can only go so far within the footprint of a single structure. True environmental impact is shaped by how entire communities are designed, how people move, access resources, interact with nature, and live together. This part explores what sustainable urban planning means. Smart density and mixed-use development. Transportation and mobility. Green infrastructure and ecological networks. Resilient cities and climate adaptation. Case studies in sustainable urbanism. 1. What is sustainable urban design? At its core, sustainable urban planning is about designing cities that are livable, efficient, resilient, and environmentally responsible. That includes reducing car dependence and promoting walkability, protecting green space and biodiversity, supporting affordable housing and social equity, designing for climate change and resource scarcity, encouraging local economies and community participation. A sustainable city should reduce environmental impact while improving quality of life for all its residents. 2. Smart density and mixed-use development. Urban sprawl, low-density, car-dependent growth, consumes land, increases emissions, and isolates communities. In contrast, smart density encourages compact urban form that reduces distances between home, work, school, and services. Mixed-use neighborhoods where residential, commercial, and cultural spaces coexist. Vertical development with public amenities built into high-density environments. Benefits: lower per capita energy and water use. More efficient public transportation. Greater sense of community and vibrancy. Reduced infrastructure costs for cities. Examples: transit-oriented developments, TOD, 15-minute cities and complete communities planning. 3. Transportation and mobility. Transportation accounts for a major portion of urban carbon emissions. Sustainable urban design emphasizes low-carbon mobility. Walkability. Safe, shaded, and connected sidewalks. Active street frontages with cafes, shops, and public art. Traffic calming measures and pedestrian-first zoning. Cycling infrastructure. Protected bike lanes and shared paths. Secure bike storage and repair stations. Bike share systems integrated with transit networks. Public transit. Bus rapid transit (BRT), subways, light rail. Mobility hubs connecting bikes, buses, trains and rideshare. Real-time tracking and accessibility for all users. EV and micromobility. Charging stations for electric vehicles. Shared electric scooters, e-bikes and microtransit. Reduced private car ownership and traffic congestion. A well-designed city moves people, not just vehicles. 4. Green infrastructure and nature in cities. Cities must be reconnected with nature to become more resilient and livable. Green infrastructure. Urban forests, green roofs, bioswales and rain gardens. Manage stormwater, reduce urban heat islands, and improve air quality. Increase biodiversity and carbon sequestration. Parks and public spaces. Accessible green spaces within walking distance of every home. Community gardens, edible landscapes and outdoor gathering areas. Social inclusion, recreation, and mental health benefits. Ecological corridors. Connect fragmented natural areas for pollinators and wildlife. Urban wetlands and rivers turned into ecological assets. Restore native plant communities and ecosystem services. Cities can become ecosystems, not just human environments. 5. Resilient cities and climate adaptation. As climate risks increase, cities must be designed for resilience, the ability to bounce back from stress and shock. Heat-resilient design. Cool roofs, shaded streets and reflective materials. Urban tree canopies to reduce surface temperatures. Passive cooling in buildings and public spaces. Flood-resilient infrastructure. Elevated structures and permeable paving. Floodable parks and plazas that absorb excess water. Resilient waterfront design, e.g., New York's Big U. Disaster preparedness. Decentralized energy systems, solar plus batteries. Microgrids and emergency community hubs. Resilient communication and mobility networks. Resilient cities don't just survive, they thrive under pressure. 6. Case studies in sustainable urbanism. Let's look at some real-world cities pushing the envelope in sustainable design. Copenhagen, Denmark. Aims to be carbon neutral by 2025. 62% of residents commute by bike. Extensive green roofs, waterfront parks and waste-to-energy plants. District heating provides efficient energy to 98% of the city. Singapore. Vertical greenery and sky gardens in high-rises. Smart traffic management and energy-efficient public housing. City in a Garden initiative integrates nature throughout the city. NE Water program recycles wastewater into drinking quality supply. Portland, Oregon, USA. Green building incentives and eco-districts. 400+ miles of bike lanes and trails. Urban growth boundary protects farmland and forests. Strong civic engagement in sustainability planning. Freiburg, Germany. Vauban district, car-free, solar-powered and community-led. Tram network with walkable neighborhoods. Passive houses and energy-positive buildings. A model for participatory, low-impact urbanism. Final thoughts: cities as living systems. A sustainable city is not a static place, it's a living system that evolves with its people, technologies and environment. It blends architecture, infrastructure, nature and culture to create spaces where people live well, use fewer resources and belong. When buildings work together in the urban fabric, through efficient design, green infrastructure and social inclusion, we unlock a future that's not just livable but thrivable. Part 8. Materials and sustainable construction. Every brick, beam and bolt matters. You can have the best design in the world, but if the materials and construction processes aren't sustainable, the building won't be either. In this part, we explore how to choose and use materials that are better for people and the planet, and how construction practices are evolving to reduce waste, emissions, and impact. This part covers life cycle thinking and embodied carbon, sustainable material choices, innovative construction techniques, waste reduction and circularity, certification systems for materials and construction. 1. Life cycle thinking and embodied carbon. Sustainable construction begins long before the ground is broken, and its impact lasts far after the ribbon cutting. Life cycle assessment (LCA). A holistic evaluation of a material or product's environmental impact across its entire lifespan. Extraction and processing of raw materials. Manufacturing and transportation. Installation and use. End of life, recycling, reuse, landfill. Embodied carbon. The carbon emissions associated with producing materials, concrete, steel, glass, etc., can make up 50% or more of a building's total emissions, especially in low-energy buildings. Goal: select low-impact materials and reduce embodied carbon through reuse, local sourcing, and smart design. 2. Sustainable material choices. Here's a breakdown of eco-friendly materials used in green buildings today. Wood, especially mass timber. Renewable, biodegradable, carbon sequestering. Engineered products like CLT, cross-laminated timber, are strong enough for multi-story buildings. FSC certified wood ensures responsible forest management. Recycled and reclaimed materials. Recycled steel, aluminum, and glass significantly reduce embodied energy. Reclaimed wood and brick give second life to valuable materials and add unique aesthetic appeal. Low-carbon concrete. Concrete is a major source of emissions. Look for cement substitutes like fly ash, slag, or limestone, calcium clay. Carbon-injected concrete, e.g. carbon cure. Concrete recycling and reuse on-site. Natural insulation. Materials like sheep wool, cellulose, cotton, denim, and cork offer thermal performance with low toxicity. Great for indoor air quality and cradle-to-cradle design. Low VARC finishes and paints. VOCs, volatile organic compounds, pollute indoor air. Look for GreenGuard or Green Seal certifications to ensure low emissions. Alternative and biogenic materials. Hempcrete, hemp plus lime, breathable, insulative, carbon negative. Bamboo, fast-growing, versatile, strong. Mycelium, mushroom-based material used for insulation and packaging. Straw bale, high insulation value, low embodied energy. 3. Innovative construction techniques. New methods and technologies are redefining how we build sustainably. 3D printing. Uses minimal material and labor. Can incorporate recycled plastic, mud, or concrete alternatives. Ideal for low-income housing, disaster relief, and experimental design. Prefabrication and modular construction. Components built off-site and assembled on-site. Reduces construction time, waste, and site disturbance. Easier to control quality and energy performance. Deconstruction versus demolition. Carefully dismantling buildings to preserve materials for reuse. Part of a circular building economy, designed for disassembly and reuse. Passive house construction. Extremely airtight, well-insulated envelope. Requires precision and high-quality materials. Leads to ultra-low energy usage, especially for heating and cooling. 4. Construction waste and circular economy. Construction and demolition generate nearly 30 to 40% of global waste. Strategies for reducing impact. On-site sorting and recycling of wood, concrete, drywall, metal, etc. Designing for material efficiency, standard dimensions, modular layouts. Material passports, digital records of building components for future reuse. Circular design thinking, buildings as material banks, not one-time products. 5. Certifications and standards for sustainable materials. Third-party certifications help builders and designers choose proven low-impact materials. Cradle to Cradle (C2C) evaluates materials on sustainability, recyclability, and safe chemistry. Declare labels, Living Building Challenge. Nutrition label for building products. Transparent about ingredients, life cycle, and toxicity. Environmental Product Declarations (EPDs). Data-driven reports on the environmental impact of a product, used in LCAs. FSC Forest Stewardship Council certifies wood products from responsibly managed forests. LEED v4 Material Credits rewards use of materials with low environmental and health impacts. Encourages supply chain transparency and regional sourcing. Case Spotlight, the Bullitt Center, Seattle, Washington. Dubbed the greenest commercial building in the world. Uses FSC certified wood, salvaged materials, and toxic-free finishes. Net positive energy and water with composting toilets. Designed for a 250-year lifespan, with disassembly in mind. The Bullitt Center shows how smart materials and construction strategies can turn a building into a sustainable